Dear students, I welcome you all for this online lecture as a part of a course on energy studies. Today we will cover the most important topic on electricity generation, transmission and storage. This is part of our unit 4 of our syllabus on energy studies. Before we go into the basics of this topic of electricity generation, we first need to understand why we need to generate electricity from different form of energy devices. So if we look at this slide and if we look into our basic usage of energy in day-to-day life, our most important form of energy that we use is in form of electrical devices such as TVs, mobile, laptop, all the devices which run internets, etc. While we also need form of energy which can perform some mechanical work such as mixtures, fan, lift, all the industrial machineries which have been utilized for manufacturing, the trains that we travel, etc. So both this form of applications, we basically need electricity. If we look into other usage of energy, which is cooking and heating and transportation vehicles. For transportation vehicles, we basically need chemical fuel such as petrol, diesel, gas, etc. While if we look into our cooking system, we basically use gas. But if we go into villages or other part, they basically use biomass in form of cow dungs, woods, etc. So these are come under the category of chemical fuels. So to summarize, it is that we require electricity as well as chemical fuel for our basic need of energy. The good part with chemical fuel is that we can able to replace all the application which is based on chemical fuel with electricity. Look at you know the cars which have been coming up or which has been forcefully put into market are all electrical cars, where most of the vehicles based on combustion engines will be replaced by electrical motors which will run on electricity. This is really need for the future because looking at the global warming and related greenhouse gases emission, so we have to convert our transport sectors into electrical vehicles. So for that we can replace the chemical fuels with electricity. At the same time, if we look into cooking and heating, if you nowadays, most of the people use induction heaters or microwave ovens for cooking. So that means that we have been slowly replacing our gas-based heating cooking systems into electrical based heating cooking systems. Similarly, for heating, if we see heating of water or heating of space, we don't require heating of space in India, but if you look at all the Western countries or even the very northern part of India, the heating of space is a very important usage of energy. For that, basically, people use hot waters, and these hot waters have been generated by using chemical fuels. However, nowadays this is been replaced by heating water by using electricity. Even our geysers nowadays we use all which are based on electricity. So if we look in this image, that it is clearly that slowly we will converge all our energy systems into electricity. So it is very important that first we have to look into how this electricity can be generated and how we can transform all our energy devices which can generate electricity. So first of all, we first look at different energy devices that we have studied so far. If we look into hydropowers, which are based on dam, see, the hydropower. If you look into wave energies, where all the kinetic energy of waves is being transformed into the usable form of energy, all the tidal energy which is been collected and then it is been released to generate mechanical energy. Similarly, the wind energy, where the kinetic energy of your wind is being utilized to rotate the wind turbines, which later on produces electricity. So if you see this, all these four form of energy systems: hydropower, wave energy, tidal energy, and wind energy, actually it produces energy in form of mechanical energy, and this mechanical energy is later transformed into electricity. Similarly, if we look into the nuclear powers, which is based on nuclear fission and fusion, and also the fossil fuels that we use or biomass, they can all generate thermal energy. You have studied in your last lectures that how nuclear fission has tremendous amount of energy released when the fission of uranium take place. Similarly, when the fusion of the deuterium and tritium atoms can generate huge amount of energy, and this energy is released is in form of basically thermal energy. Similarly, if we look into fossil fuels and biomass, we can burn these fuels and generate thermal energy out of it. Solar thermal, which is also one of the very important applications to generate thermal energy, where you use a concentrated solar power by using a large mirrors, and this concentrated solar power is being used to heat the water or any kind of chemical salt, which later on will be used in the turbines to generate electricity. Fossil fuels and biomass are also a good form of chemical fuels which can directly burn and generate electricity out of it in generators. The only single form of energy device, which is solar cell, can directly produce electricity. Solar cell, as you know, that it is basically in form of semiconductors where absorption of photons can generate electron and hole pair, and this, by generating an electric field by p-n junction, we can separate this electron and hole pair and generate electricity directly out of this. So except for this solar cell, if you see the other, all the other form of energy device, they either produce energy in form of mechanical energies, in form of chemical fuels, in form of thermal energy. But it is very important that all these other three form of energy has to be converted into electricity, which is basically what we use in our daily life. So how we can do that? So first we will study on how electricity generation can be done from the mechanical energy. So this is basically we have covered in our past lectures, but just wanted to repeat here that it works on the Faraday law of induction, which clearly states that if you put a conductor in a varying magnetic field, the current will flow through that conductor. So that means if you look at this diagram here, you can see there is a loop of wire and there is a permanent magnet which generates magnetic field. So if I just rotate this loop of wire, okay, so it will, each part of the loop of wire will be in a different magnetic field at different time. So each point in the loop will be under variation of magnetic field, which will allow the electron to move across this loop and produce electric current. So this is how basically electricity is being generated through your mechanical energy. Mechanical energy is what? Here is the mechanical energy where we just rotate the loop of wire in the in between the permanent magnet, so that each time there is a change in magnetic field when it rotates, and because of that we can generate electrical current. So this is basically how it works. If we just look into in form of equations, you can see directly here that if I use this planar loop of wire that I've used in the into this diagram as an conducting wire of an area of A, it is rotating with a constant angular velocity of omega in a uniform magnetic field of B, and suppose this loop consists of n turns, okay, and sustains an angle of about theta, which is equal to omega t to the magnetic field, where t is the time. So the magnetic flux which will intersect with the loop is given as such, which is NBA cos theta. This is the because of the angle which it makes with the loop magnetic field. So in this case, theta, as I've told you, is omega t here. So we just substitute omega t here, and by Faraday's laws of electromagnetic induction, the work done will depend upon how much the magnetic flux is being changed, or we can say it's the work done or the electromotive force is equal to the rate of change of magnetic flux. Thus, V is equal to minus d by theta upon dt. So this can be equated in form of NBA omega sine omega t. So you can clearly see that voltage that is being generated, which is the electromotive force, is proportional to the sine omega t. So in and the voltage that we are generating, okay, which will be in form of a sine wave. If the electric circuit is connected through the ends and having a resistance of R, we can also find out the current out of it. So current is nothing but V upon R. So if we substitute V, which is NBA omega t sine omega t upon R, so we can equate into this equation where I0 is NBA omega t. So if you look at this equation, I is proportional to sine omega t, okay, and most importantly, you can see that I is also proportional to N. So higher the number of turns, more current that you can generate within this loop. Okay, so just remember this point, and that is the reason when you see a generator, or I don't know if you have seen uh, a motor winding, you can see there is a coil of lot of copper wire that is been wounded around the conductor, and each turn, okay, the number of turn is nothing but n here. So more the number of turns, more will be the current that will be produced through this. So that is the reason you will not find a single wire, but you will find a bunch or a loop of wires having lot large number of turns into this conductor. So are we clear on this part, where how the electricity is generated where due to the mechanical energy of movement of your wire loop in a magnetic field, we can generate current into the loop, and the amount of current that is being generated will depend upon the turns which are there into that wire loop. At the same time, the waveform that is being generated of the current, which is nothing but sine wave, and that's the reason we always call this electricity generation as a alternating current, because we produce a sine wave of this, which can go from from zero to positive amplitude to negative amplitude. Now we can look into the device that has been practically used to generate electricity from the mechanical energy. So if you consider, if you just remember the working principle of your hydropower, tidal energy, wave energy, and wind energy. They all just produced, they just convert the kinetic energy of the fluids into the mechanical energy of your turbine. Okay, and turbine rotates, which is this part. So this is the shaft of your turbine. Okay, and which collects all the kinetic energy where the this turbine shaft is been connected with the fans, and this fan collects the kinetic energy of your fluids, and this turbine shaft rotates. Now, how does a generator look like after the rotation of this turbine shaft? This contains basically uh, three main parts. One is your rotor, which will rotate. Okay, one is stator, which will be, you know at a which will be surrounding your rotor, but it will be at a stationary position. At the same time, there will be also a cooling system around this stator, which will able to cool the most part of your generators. Now, where is the magnet here and where is the conductor? So magnet basically in this case is in this rotor. So it is not the permanent magnet that is being used. Basically, we have also a coil magnet that is being used here, where you use a lot of winded materials. Okay, and we pass the electric current through this coil, which is basically an electromagnet, and it will generate magnetic field. And since because of this rotation, the magnetic field will always vary in the different part at time instant t, while stator is nothing but a coil of wire. Okay, so if you see the electric current, the wire which is connected, one which is here and the other one which is connected on the other side here. Okay, so this between this there is a large number of coils which is been produced by winding the wire of copper. So basically this, in this case, stator works as a conductor while the rotor works as a magnet, which due to the rotation will produce a varying magnetic field. And since the length of this wire or length of the copper wire which is winded around the conductor is so huge that when the current flows through it, because of the resistance and because of the length of this wire, there's a lot of heat that is being generated. And to maintain the temperature of this and maintain the loss due to heat, we always have a cooling system surrounding it. If you have seen the mechanical motor, the water pumps, basically, which actually does the reverse of what I'm showing here as a generator, where we pass an electric current through to my stators, and because of this electric current, you know it will produce magnetic field, and because of the magnetic field the rotor will rotate. So this is basically a reverse mechanism that takes place in water pumps. There also, if you can see the outer body, it contains some metal uh, heat exchangers. Okay, this metal heat exchanger is nothing but a cooling system for them. So, and when a motor is running you cannot touch it, it's quite heated. So you have already seen it, means, I don't know if most of you have felt it, but yes, it is very heated and it do require a cooling system. Similarly, in generator as well, you require a cooling system. So I hope it is clear that we have a mechanical movement of your turbines, okay, which where your electromagnet is loaded, which generate magnetic field, and because of this rotation motion, this magnetic field will always vary at different places at for time instant t. And because of this varying magnetic field, the current is being generated into the stator, which is basically nothing but a coil of wires. And this electric current which has been generated through this is extracted and it is used as an electricity. So this is how your all your generator works based on your mechanical energies. I hope it is very clear because this is very important for the electricity generation. All the electricity generation is being done through this basic concept. Now, it is very important to understand, what we use in our form of electricity. I hope you have seen electricity which has three phases. Basically when we I don't know if you have seen your electrical board, or wherever you stay in your buildings or apartments, where there are main lines of electricity, you will always see three colors of your wires. One is red, yellow and blue. Basically this is nothing but it is three different phases. What do you mean by three different phases? This is nothing but each three wire is producing same power, okay, which is producing same amount of voltage and same amount of current, but the phase is separated by 120 degrees. You're getting my point? See, basically, when I want to illuminate my bulb, or I want to start my fan, I basically just connect to my plug, one of my plug, and I just run my make my switch on and my bulb will be plugged. So if you can see here, the bulb can be plugged only through one of these phases. Similarly, the socket or the electrical board that we use, it is also connected to a single electrical wire, okay, and so it is connected to a single phase. Okay, so for this applications, the normal applications, basically we need a very low power consumption, so even a single phase will be okay. But if I want to run a pump, see the water pump, you can see this water pump. For this water pump, mainly we require three phases. That means that all the three electrical lines will be connected to my motors. That means all the three wires, which is red, yellow and blue, will be connected to my electrical motor, and which can generate power voltage of about 400 volt. Why you require three phase? Three phase is basically nothing but it produces more power, okay, all the power, more power than the single phase. Now how this is being generated, how three phase is being generated, okay, it's quite simple. It is generated again into my generator. Here what we have is that the rotor and the stator, okay. Here we have a single rotor, but we have a three stators, okay. So if you see, this is the, if you look into this, there is a three stator. One stator is this one, the other one is this one, and the third one is this one. So if you see the three stators here, which have been separated by an angle of 120 degree, okay. So when a rotor rotates, okay, the magnetic field, the varying magnetic field will generate the current, okay, equally in all three status, but with different theta or different sine omega t. And that is the reason, you will get a sine wave in all three rotor, all three status, but all these sine waves will be having a phase difference of 120 degree. You're getting my point? Now what is so important about this three phase electricity? If you look at this phase, the waveform diagram of three phase, if you see, this is the phase one, black, which has been put starting from zero and this go. while this is blue, red is phase 2, blue is phase 3, and you can see the angle between all three phases is about 120 degree. What I look when I look into this waveform, if I just sum this waveform together, because see in the end, when I connect all three phases together into my a single application, all these phases will be add up. So my overall power in this three phase electricity will never go to zero. See, if I consider only the single phase, if I consider, let's say, this black phase, it starts from zero. Okay, after 120, after 180 degree, it again comes back to zero. Okay, it again goes. So in this case, the current will come to zero at certain point. But if I consider all three phases together, and if I take the summation of this three phases, or the summation of these waveforms, okay, you will see that I will, at any point, I will never go to zero. You can just look into this. Take any point in this waveform. Take, let's say, at 90 degree. 90 degree, you can clearly see the phase 1 is at high, while phase 2 and phase 3 is at minus zero point 0.5. So if you just add it, it is about zero point 0.5. But if you consider at 180, okay, if I consider at 180, 180, again, phase 1 is going to zero, but we have still powers which can be generated through phase 2 and phase 3. Okay, while if I consider even at, let's say, more than 270, where red is coming, where the phase 2 is going zero, even at that point, phase 1 and phase 3 will be at certain high points where which can generate power. So what I want to say is that your power will never go to zero, so you can consume continuous power with three phase electricity. At the same time, it also requires 75% of your material is required to conduct same quantity of power as in single phase. So the material that is being used, it is 75% less, okay, what we use for single phase. So that is a good advantage of a three phase electricity generation, and even electricity transmission. This all three phases is been transmitted in form of three different wires. If I will come to this point later on when we talk about electricity transmission. But if you just noticed that when we have electricity transmission through your towers, you will always see a three lines or three wires, going and coming back, and there's a fourth wire which is at the top of the tower. All these three wires actually basically is nothing but transmitting electricity of three phase. Okay, 1, 2 and 3 wires, phase 1, phase 2 and phase 3, and which has been connected together later on to produce the three phase electricity. So are we clear on three phase electricity? It's very important to understand that when generator are being utilized, it always produces electricity in three phase, so that we can generate more power. At the same time, when utilizing this thing, our power will never go to zero. Now, how to generate electricity from chemical fuels and thermal energy? We have clearly seen that how mechanical energy can be transformed into electrical energy by using generators. But how chemical and thermal energy can be converted into electricity? So basically, we have studied this in our past lectures, where your chemical fuels and where chemical fuel is been converted into thermal energy, and then thermal energy has been converted into mechanical energy, and this mechanical energy is later on is converted to electricity, and this is done through your thermal power plants. If you remember all your thermodynamics or the cycles, thermal cycles that we have studied, which is nothing but your Carnot cycle and Rankine cycle, where we use four main components. One is your compressor, then we have boilers, we have uh, turbines, and then we have condensers, and this all four is been connected in cycle so that the electricity so that we can able to produce a mechanical work, right? If you remember that, in boiler we just boil the water, convert it into steam, and this highly pressurized steam can be put into turbines so that the blades of the turbine can be rotated and can produce mechanical energy. And we have already seen that how this mechanical energy can produce electricity. So that means we are generating nothing but we are burning chemical fuels, which is in form of either coal, gas, or any other fossil fuels, which can able to generate thermal energy. This thermal energy is in form of steam, and this steam is able to convert into mechanical energy by rotating turbines, and later on this turbines, the mechanical energy of this turbine is been converted into electricity by using your generators. So this is how the whole setup that we have already studied is been taking place. So chemical fuels can directly be converted into electricity. So all your, even in your nuclear power plants, you have seen the nuclear power stations or the power plants where your fission reactions have been taken place into your boilers or the water, and all the heat that is been released from the fuel rods due to fission is been able to convert the water into steam, and this steam is later been used to rotate my turbines to produce mechanical energy, and this mechanical energy is later on converted into electricity. So similarly, your nuclear power plants can be directly convert into electricity. Your thermal power plant, as I've told you, can be also used to convert electricity. Your solar thermal power plants. Solar thermal, basically you have not studied yet because we have not covered the lecture on the solar energy. But it is the same principle that it has been used as the thermal power plants. Only the boiler part or the thermal energy that is been required to evaporate my water into steam, that thermal energy is been provided through my concentrated solar mirrors. Okay, what I'm trying to say is that you have lot of mirrors. Okay, and this mirror is able to reflect my solar light and able to focus at a single point, okay, which can generate huge amount of thermal energy and which is able to use as a boiler for conversion of my water into steam. Okay, we'll come to that later on when we study the solar thermal part, but anyhow, right now it is quite clear that all the thermal power plants that we used, okay, it's able to convert my chemical fuels into thermal energy, and the thermal energy is converted to mechanical energy and so on into electricity. So I hope this is quite clear about the electricity generation that from the electrical devices. Okay, so students, this was the first part of this PPT. Later on, we'll take the next part, which is on energy or electricity transmission that has been taking place. So thank you.